Hey everyone, and welcome. Have you ever looked at a number and just thought, okay, but is that good? Is it high? Is it low? A single data point, a raw score, it really doesn't tell you much all by itself. So today, we're going to dive into the statistical tools that give those numbers real context and meaning. So let's start with a classic puzzle. You've got two students. One gets a 1200 on the SAT, the other gets a 24 on the ACT. Now, who actually did better? They're two totally different tests with completely different scales. How can you possibly compare them fairly? It really feels like comparing apples and oranges, right? Well, this is exactly the kind of question we're going to answer.
And that's because, raw scores can be seriously misleading. The secret isn't in the number itself, but in where that number stands compared to everyone else. And this is the core idea of what we call relative position.
All right, so our first stop on this journey is a really simple but incredibly powerful idea: ranking. How do we figure out where one value stands in a whole crowd of them? Well, the most common way to do this is by using something called percentiles.
A percentile tells you the percentage of data points that fall below your specific value. And here's the part you really got to remember. A percentile is all about your rank, not your score. Getting a 90% on a test is completely different from being in the 90th percentile. So for example, let's say you're in the 90th percentile on a test. First of all, nice work. That means you outperformed 90% of all the people who took that same test. See? It's a really powerful way to understand how you did relative to your peers, no matter how hard or easy the test was.
Now, a specific type of percentile that you're going to see all the time are quartiles. You can think of them as kind of the VIPs of the percentile world. They chop up the entire data set into 4 equal quarters, which gives us a really quick snapshot of how the data is spread out.
And it's actually pretty simple. The first quartile, we call it Q1, is just the 25th percentile. Q2 is the 50th percentile, which you might already know is the median. It's the exact middle of the data. And Q3, the upper quartile, that marks the 75th percentile. See? Simple, clean, and super useful.
Okay, so why are these quartiles so important? Well, because they give us this amazing tool for measuring the spread of our data. And even more exciting, for hunting down those unusual values we call outliers. This is where we get to meet the interquartile range. The interquartile range, or just IQR for short, is simply the range that contains the middle 50% of your data. And its superpower is that it's robust. Now, that's just a fancy stats way of saying it doesn't get easily thrown off by a few really high or really low values. It's focused on the heart of the data.
And the calculation? It could not be easier. You just take the third quartile, Q3, and you subtract the first quartile, Q1. That's it. The number you get is the spread of that middle chunk of all your data.
But just measuring the spread is kind of the opening act. The real magic of the IQR is how it helps us systematically find outliers. Those are the data points that just don't seem to fit in. They could be mistakes, or they could be the most interesting part of your whole data set.
So here's the standard recipe for finding them. First, you calculate your IQR. Simple enough. Then, you multiply that number by 1.5. You take that result and subtract it from Q1 to get what's called a lower fence, and you add it to Q3 to get an upper fence. These fences basically create the boundaries for what we consider normal in this set of data. So in a nutshell, any data point that falls below that lower fence or goes above that upper fence gets flagged as a potential outlier. It's a simple, really solid rule that tells us which points deserve a much closer look.
Now, the IQR method is fantastic, especially when your data is a little lopsided, but what if we need a bit more nuance? What if we want to know how much more unusual one score is than another? For that, we need something I like to call the universal translator of statistics. See, percentiles are great for telling you your rank, but they don't tell you anything about the distance between the scores. Was the person just ahead of you a tiny bit better, or were they miles ahead? To understand that distance, we need the z-score. A z-score standardizes any value, telling you exactly how many standard deviations it is away from the average or the mean. And a standard deviation is just a way of measuring how spread out the numbers are. So a z-score basically says this point is this many units of spread away from the average.
Now, the formula might look a little intense, but it's actually pretty simple. You take your value, you subtract the mean, which is often that Greek letter mu, and then you divide that whole thing by the standard deviation, or sigma. With that one calculation, you can put any score from any test onto the exact same standardized scale.
And interpreting a z-score is just as easy. If it's positive, your value is above average. If it's negative, it's below average. And a z-score of 0? Well, you are perfectly smack dab in the middle, average.
Okay, let's go all the way back to our original question, SAT versus ACT. Once we calculate the z-scores for both, the answer becomes crystal clear. The SAT score of 1200 is 0.75 standard deviations above its average. The ACT score of 24 is only 0.64 standard deviations above its average. So, because 0.75 is bigger than 0.64, the SAT score of 1200 is the better performance, relatively speaking. The z-scores translated them for us perfectly.
So, we've just covered two fantastic methods for finding outliers and comparing data, the IQR method and the z-score method. The big question is, which one should you use?
Well, the choice really comes down to the shape of your data. The IQR method is your absolute go-to for data that's skewed or lopsided, because it's robust, it's not easily influenced by those extreme values. The z-score method, on the other hand, works best when your data is nice and symmetrical, kind of like a bell shape. But it is more sensitive because the mean and standard deviation it uses can actually be skewed by the very outliers you're trying to find. So the key takeaway here is this. Before you start hunting for outliers, you have to just look at the shape of your data. Is it symmetrical or is it skewed off to one side? The shape of your distribution is what tells you which tool is going to give you the most reliable answer.
So, let's wrap this all up. Measures of relative position are the tools that transform raw, kind of meaningless numbers into powerful insights. Percentiles and quartiles, they're all about ranking, telling you where you stand in line. And z-scores, they're all about comparison, letting you see how you measure up on a universal, standardized scale.
You now have the fundamental tools to look at any data set and understand not just what the numbers are, but what they actually mean in context. So the only question left is, what hidden story are you going to uncover in your own data? Thanks for joining me on this explainer.